Those who are online, are you able to see my screen?
Yes, sir. But I can't see your screen again.
Like you're not able to see the PPT?
I can just see that class one learning room has started screen sharing. Can't do that.
Okay. Open multiple devices. Now is it visible?
No, sir, it still says the same.
Now is it visible?
Yes, sir.
You're able to see the PowerPoint?
Yes, sir.
Perfect. Yeah. So what were the concepts that we saw yesterday?
Sir, till SI unit.
So till SI units, and we saw till supplementary units, right? So we saw till this concept. Am I right?
Yes.
So can you tell me what are fundamental units? Raghav, can you tell me? No, what do you mean by fundamental units? Or used to build other units. Okay. So what are the other units that are built? They are called as derived units. So what are the fundamental units we learned in the SI system? What are fundamental quantities? No, what are the fundamental quantities which we saw in the SI system? There were 7, right? Fundamental quantities. Understand the difference between quantity and units. Santosh, you tell me. These are the quantities. Amount of substance. Yes. So what are the units corresponding to it? Candela. Mole. And you forgot electric current. Electric current is ampere and the symbol used is capital A. Right. And what are the supplementary units? You have it in front of your eyes. Yeah, what are they? So one is for the plane angle and the other is for the solid angle. So for plane angle, how, what are the unit we use for plane angle? It is radian, and for solid angle we use steradian, right? So till now, whatever we saw was the building block of this chapter. Now, after this, what we need to know is we need to understand how the measurements are taken, right? There are some experimental parameters based on which the measurements are being taken, something like this. I'll show you the outline. Okay, but before that, I need to give you what are the practical norms that we need to keep in our mind for writing the SI units. So you can write down this heading. So the next topic that we are going to see is what are the practical norms for the use of SI system, right? First thing is unit of every physical quantity that we are going to define should be represented according to its symbol, right? We know how the symbols are written. For meter, you write M, for second, you write S. Like that, you need to follow these conditions. Okay, the first one is unit of every physical quantity should be represented according to its symbol. Second thing is no full stop should be used at the end of the symbol. Okay, you should not use a full stop. For example, you will not write 5-meter dot unless it is going to be the end of the statement. Even that full stop is going to have some space, but this full stop should not be a part of the unit itself. That is the meaning. Okay, so no full stop should be used within or at the end of the symbol. Why I said within is because when I say kilogram, you should not write it like this. It is just kg, kilogram. Okay, you should not write it like an acronym. That is, you simplify it and then write it like a split word. It is not kilogram, it is written as kg, like this. Okay, for example, if you take this kilogram, you should write it as kg and should not write it as kg dot or k dot g. Okay, and the third part is symbols for units do not take plural form. For example, if it is 1, we write it as meter. If it is more than 1, if it is 2, you should not write it as meters like this. If you write something like this, the whole meaning will change. It will become millisecond. Okay, so it will become millisecond. So this one should be avoided, irrespective of whatever is the value of the quantity that you're trying to measure. Okay, so for example, if you take meter, so meter is used to denote many meters also. That is the meaning. So M is a symbol that is used to denote if you have many meters also, right? And the fourth one is the units of physical quantity and numerator and denominator should be written as 1:1 only. If at all you have a physical quantity where you have that to be written in the form of a numerator and denominator. For example, if you take acceleration, you write it as meter per second square so that you have one numerator and one denominator. You should not write this as meter per second, which is for velocity per second. Don't do this mistake. You should not write it like this. Okay. If you take the acceleration, right, it should be written as meter per second square or meter second power -2. But you should not write it as meter per second per second. That is the meaning of this. It should be written as a single ratio. Clear? And the next point that we need to keep in our mind is if you write the full name of a unit, right? For example, meter, use a symbol M. If you want to write it completely, then what we do is, so if you write the full name of a unit, even if it is even if it is named after a scientist, you should not write it in capital because here we are not going to follow any grammar or something. For example, if it is Newton, you should not write it as NEWTON. Rather, you will write it as small NEWTON. Even if it is the name of a scientist, you write it you start with the lowercase. Okay, it is not written with a capital letter, but the symbol for that unit has a capital letter. So understand the difference. So the name of the scientist, when you write it in expanded form, you start with lowercase, but the symbol for this will have uppercase. So Newton, you write it as capital N. That is the meaning of this. Okay. For example, if you take the unit of force, it should be written as Newton, but the symbol should be capital N. Similarly, if you talk about the unit of pressure, it is the name of a scientist, right? So how do you write it? So it is Pascal, right? But you start with a lowercase. Okay, you should not put it like this. You put it in the lowercase, Pascal, and its symbol is written as PA. The dot is not a part of the symbol, it's the end of the statement. Okay. Similarly, what is the other unit you can think of? You can think of ampere. Ampere is named after the name of after the scientist, so which is written as capital A. Right. Similarly, you will be seeing another unit called as Coulomb. COULOMB, which is again written in capital C. I hope you're able to get some perspective, right? These are some important points to be kept in your mind when you write unit for any physical quantity. Okay, so please make a note of this. Shall I proceed to the next topic? Yes. See, listen. When it comes to the next part, see, first we understood that in real time, we are going to take some measurement. And when you take some measurement for us to communicate with others, you need to attach a tag called as a unit with it. And we saw what are the rules to be followed to write the unit, right? The next question is, obviously, we need to understand how to take the measurements. So what we do is we see the concept of measurement for three important parameters like length, time. You can first listen. So you will see for mass, length, and time. So where I'll just give you the outline of this topic. This is not what I'm going to discuss now. Okay, see, if you look at the topic, right, how are the measurements of large distances done? See, for example, we are on Earth. If you want to measure the distance of a planet, so there's going to be an approximate value. How are we going to use the concept of mathematics to measure the distance? Okay, through some method, they are going to measure it. So this is the outline. As of now, just listen. I told you, no. So this is one thing. Similarly, there is another method. Okay, where you want to measure the size of the planet. That is also related to length. They use some trigonometry. Basically, they are using the concept of radian definition, which I told you yesterday. If you know this angle, the arc length divided by radius is going to give you the values. Okay. Similarly, there is another way to measure it. There are different ways. Similarly, when you calculate the mass of a substance, when I ask you to calculate the mass, there are different ways in which you can do it. You can ask me a simple balance. You say, sir, you give me a simple balance, I'll put it on the balance and I'll measure the mass and tell you. That is one way. Or there are other ways you can think of. You can think of different machines that can calculate the mass and give you the answers, right? Or theoretically, what you can do is you can just take an object, drop it, calculate the time it is taking to travel, use the mathematical equations and tell me what is the value. That is another way, right? Similarly, for time also, what you can do, if I ask you to calculate the time, so in the older days, what they used to do is they used to calculate it with the help of sundial, right? They used to calculate it with the help of the motion of sun. So depending on the position of sun, they used to tell the time. Then we started developing these clocks and watches and everything, right? So all these things are related to measurements, right? So now I'm going to discuss an important topic. So I'll come to this part at the end because this is very, very, very theoretical and not that interesting. So I'm going to talk about some important concepts after you take a measurement, right? See, suppose I give you any task for that matter. Okay, let's say this book is there. Okay. If this book has to get printed in this kind of a format, then there are certain measurements you need to give to the person who's going to print it, right? So what do? Suppose I'm not using a very hi-fi measurement device or something. I'm just using a normal plastic scale where this is something you use in your day-to-day life, right? So if you look at the calibration that is there on it, what values does it give? So the scale has two sides, right? So the scale has two sides, obviously. One of the sides, it has centimeter. So is it only going to give you centimeter or any other quantity also? Inches is on the other side. I'm talking about this side. So it can give you centimeter, also millimeter. See, for example, if you write 10.5 centimeter, what is the meaning of it? It is 10 centimeter and 5 millimeter, right? So that is the way you measure it. So that is the way you can communicate to the person. Or else you take this side. Let's say you are a person who's comfortable with the concept of inches. Then you can use the other side and measure it. So what I'm trying to say is, if suppose I'm giving you a task, let's say I'm giving you a design. Say you design something and give it to me so that I want to cover this book. You take the printout and cover this book. So what you will do, obviously, you will ask me for a scale, right? You will just try to place one of the ends here and measure the other end, right? So it will come to some value. It will come somewhere around 8.5 inches. Okay. Or when you measure it in terms of centimeter, it is going to give you some other value. In a similar way, what will you do? You will measure the vertical. So it will come somewhere around 11 inches. Are you able to understand what I'm trying to say? So it comes to 11 inches. Right. So what is the dimension of this? It is 8.5 inch by 11 inch. So you open a software, you design something like that, and you give it to a person. Right. But when you do this measure, Okay, when you do this, when you take this measurement, do you think it will be 100% accurate if there is something that you're missing? For example, if I keep the scale like this and measure, okay, maybe I'm accurate. But can you give me a confirmation that you exactly kept it at 0 degrees? Means, did you exactly keep it parallel to this? Humanly, what could have happened is you could have done a mistake by doing something like this. You could have tilted it. No? You're able to understand what I'm trying to say. These are all human errors. It is possible. Okay. So when you do something like this, when you're reporting the answer, you're missing something. Right. So what do I need to print this book perfectly? I'll tell you what has happened. See, for example, if you look at this part, right, are you able to observe some defect here? Are you able to observe some defect in the finished piece? What is that you're able to see? One thing, so alignment has got missed. It is something, the mistake that was done on the printing side, and when they cut it right, they cut it wrongly. In a similar way, when you look at this part, right, when you look at this part, are you able to observe any error? I'm able to see something. So if you see the edge, right, it is actually not coming horizontally, it is tilted. See, for you to see it, this book specifically has an error. You're able to see this part, and this one is bent. Breathe. So this has something to speak about two quantities. Okay. So did you understand what is measurement of a real-time example? So something we face challenge with these kind of measurements. So when you do this measurement, there are two things that need to be kept in your mind. One is accuracy, and the second is precision. Okay, this is something I want to inject it properly in your mind, because most of them don't understand. If you see the words, right, accuracy and precision, they feel it is the same. Are they not looking similar? It feels like, what is the difference? They both look to be the same, but there is a minor difference. Okay. So when I talk about accuracy, I'm trying to say how accurate my measurement is. In the sense, I know the value, I know the size of this paper even before it was printed. I know it was 8.5. Right. But what has happened here? The machine did not take the accurate value. That is why it cut in a wrong way. Right. So there is one thing. So when you already know certain values, and when you try to measure the same value experimentally, right? So observe this. Accuracy of a measurement is a measure of how close the measured value, means how close the value you are calculating experimentally is close to something called as true value. True value is something which you already know. So what is happening here is, I already know the value, but I did the measurement. Instead of me getting the value as 8.5 inch, I'm getting it as 8.4 inch. Like, I repeat the experiment multiple times. Instead of 8.5, I got it as 8.4. Then there is some error in my measure. Or I would have got it as 8.45. There is some error in my measure. So it is not exactly 8.5. You're able to understand? And this is what you will exactly face in the lab. I told you yesterday, right? You will exactly face these kind of errors. If you don't get errors, then you're wrong. You will get errors, because all those calibrations that are given to your machine are calculated using machines. But we are doing it manually. When you do it manually, definitely errors will be, due to whatever reason it might be. We'll see what are the types of errors in the subsequent topic. But let's try to understand what accuracy is. Are you able to understand? So basically, you do an experiment, you measure a value, you already know a value. How close these two values are is going to give you the accuracy of that measure. Am I clear with that? Okay. So that is the meaning. Then next question is, what is this precision all about? Suppose, let's take the same example of this book. When I try to measure using the scale, right? I told you I'm getting 8.5 inches. So if I keep it like this, I'm getting the 8.5 inches. Okay. You saw how the lines are going to be. So if this is one reading, you have some gap between the subsequent readings. So if your end to end falls somewhere exactly at this line or this line, you will be able to tell the number. Are you able to understand what I'm trying to say? See, let's forget about inch as of now. Let's say I'm taking in terms of centimeter. Okay. I keep my 0 here. I'm trying to measure it here. So what is the number you are able to see? So 21, is it exactly falling on 21? Where is it? Or is it exactly falling on, can you tell me with the decimal value 21 point? Is it exactly falling on 2 millimeter? No, right? Is it between 1 and 2 or it is between 1 and 2, right? So you're able to understand. So this calibration is in such a way that you have, he's saying this 20 is 21 is here and your reading is falling somewhere over here. At that time, how will you report the answer? Because I need to be precise, right? Or else machine will not understand. If I tell it 21.1, he cut 21.1 and give me, then what would have happened is I would have had some gap here when I got it printed. Then the book, most shabby work that I can do, right? So when I report the answer, I need to keep something precise. In the sense, what do I need to know? I need to know how much is the gap that is existing between 1 and 2, right? So if I use this scale to measure the length of it, right, the horizontal length of it, I'm getting somewhere between 21.1 and 2. I don't know what is the number. So if it is closer to 1, I will say maybe 21.1. If it is closer to 2, I'll say 21.2. If it is somewhere between, approximately, I can say 21.15. That too, I'm only approximating. I'm not 100% sure. But if I need to take a precise reading of this, whose help do I need? Is it my mistake that I'm not able to report that answer? It is a mistake of the scale. Because it is designed in such a way that you have the calibration only between 1 and 2. I don't know what is the intermediate number. What if I had a better scale in my hand where the distance between 2 millimeters is also broken into 10 even parts? Maybe I would have been able to report the answer. So you told no, there also a challenge will occur. What will happen? Even in that, if it is falling between two readings, again you will face a problem. So if you keep zooming in, right? If you keep zooming in, there'll be one particular instance where it will exactly coincide with that number. Right? So we don't know, it is only a possibility. But what we are trying to achieve here is we are trying to be as precise as possible. I'm talking about accuracy. We are trying to be as precise as possible. So if I report the answer using the scale, using the plastic scale that I have in my hand, I would have reported the answer as 21.1 and left it. Okay, of course, I'll add the unit 21.1 centimeter. What if I had a better scale? Maybe I would have reported the answer as 21.12 centimeter. What if I had even more better scale? I would have reported the answer as 21.123 centimeter. So among all these readings, what is it you're able to understand? Among all these readings, so more is the decimal value that you're able to report to the person, more precise your answers. So who is deciding the precision of that? So who is deciding the precision? Is it you or the measuring device? It is a measuring device. So accuracy has something to do with the way you perform the experiment. Precision has something to do with the device which you are using to do that measure. Am I clear with what I'm trying to say? You're clear? See, similarly, if you think of, let's say, a cake. Okay, let's say I'm giving you a task. Birthday is over. The birthday boy or girl has cut the cake. Somebody's birthday today? Somebody's birthday? Illa. Okay, I give you a knife. Okay, you generally get that plastic knife when you buy something. No? When you cut with that, okay, you would have seen the thickness is more. When you cut it, at the edges, there'll be a slight bend like this. You would have not observed, next time observe them. Okay, there'll be a slight bend like this. The cake will get bent because of the pressure. What if I give you a better device and ask you to cut it? In the sense, if I give you a sharp thread and I say, keep the thread like this and just pull it like this, which one will give you a better shaped cake? Because you're applying more pressure with lesser area. Is that not what you're using? So which is more precise device? The thread. So that's what precision is. So why I told this example is don't restrict your mind only to physics. So precision occurs everywhere. Okay, if you want that perfect finish for anything, you need to be precise. That is the meaning of it. That is what I'm trying to say. Am I clear with this? So is this a precise finishing? It's a very shabby work. It's not a precise finishing. But if you see this side, right? So here they have cut and everything, right? It is sharp actually. It is actually cutting my hand. If I rub it fast, it definitely you can see blood in my hand. It is that sharp. But it should be precise means they should give the clean finishing on the other side. You're able to understand? So that is the meaning of precision, and accuracy is something with the measurement that you, something with the technique you follow to take the measure. Are you able to understand? So just make a note of the definitions. True value, na, see, some reference value which you already know. It cannot be. How are machines accurate? They're the most inaccurate things on the planet. Nothing is accurate. There is nothing like accuracy. You can only find the nearest value. There is nothing like 100% perfect in this planet. You will have defects, including us. Everybody will have. Okay. So don't write everything. I'll tell you what you're supposed to. So who decides the accuracy? The way we do the measurement. Okay. Who decides the precision? It is a measuring device, right? So for a measuring device, right, there is something called as least count. So what do you mean by least count is the least value any measuring device can tell us. For example, if you take the scale itself, after 0, right? So between 0 and 1, you have 10 lines. So immediately after 0, what does the first line that is there on this indicate us? It is 1 millimeter or 1/10 of a centimeter, right? So the least count of this device is 1 millimeter. Means it cannot give me a value below 1 meter. If I am measuring the length of any device which is less than 1 millimeter, this device cannot help me with. You're able to understand? So what does the least count mean? The name itself is suggesting least count. Okay. The immediate value that is occurring after 0 is what is called as least count. That is one way of perceiving it. Or the other way of perceiving it is the distance between two successive readings is also called as least. So you take any random point. If you take one line as the first reference line, right? what is the distance to the immediate line that is available after it. So the distance between them is going to give us the least count. Okay, so I'm not going with the book definition exactly. In your book, they would have told it as the number that is immediately occurring after 0. But I'm just trying to tell you, if you measure the distance between any two subsequent lines available on that device, that's going to give you the least count. Okay, so here they have given an example, right? So if you take an example, we have the digital watch, right? So when you look at the digital watch, what are all the values it can tell us? So it can give us the seconds. If you want to be more precise, it can give you the millisecond also, right? So if I take this kind of a device, is very precise. Can I call it as precise? Because it is not stopping with minutes, it is giving me seconds also. It's very precise because it has a least count of how much value. So what is the least value it is able to tell me? The last one, that is seconds. If at all I give you a digital watch where it is able to measure millisecond also, if I ask you to compare the precision of both these, which one millisecond will be more precise because its least count is millisecond. So lesser is the value of least count, more is the precision of the device. So that's how it is helping, no? So for example, the least count of this is for 21.1. What is the least count I'm able to see? Look at the last digit. It is 1 millimeter. What about this? So 1/10 of a millimeter. Here I'm able to say 1/100th of a millimeter. This is more accurate. Means this device, if at all it is existing, right, between 2 millimeter lines, you will be able to see 100 lines. It's very, very difficult for us to see with the naked eye. That is why they will not devise such something like that. You're able to understand? So on the other hand, if you look at the normal clock that is available, right, what is it going to tell us? So if you look at the grandfather clock, means the time there used to be no seconds. It will only show you the hours and the minutes. So if you have something like that, let's say the time is reported like this, comparatively it is less precise. I'm assuming that by now you would have understood what is the meaning of precision, right? So for the least count of this device is going to be 1 minute, which means it is less precise compared to this. So always when you speak about precision, it's a comparatively, right? So that's what they have given there. Next is, as I told you. So this accuracy and precision is clear now. The next question is, when you take a measurement, what are the different kinds of errors that we are going to get? So that's the next topic. So the next topic that we are going to see is errors in measure, right? So when different physical quantities are measured in a lab, right, with the help of different apparatus that is given. So depending on the experiment, you are going to use the apparatus. There would be some inaccuracies in the measure. So what you need to do is, you should not report the average value and leave it. What do I mean by average values? Generally, when you do an experiment, you don't stop it with one reading. You try to take multiple readings, and then what you do, you take the average of it. That is how they ask you to do. No, why you need to do that is because each time you observe, you will get different value. Every time you will not get the same value. So if you take that average value is what is said to be true value according to that experiment. I told you the true value in the case of accuracy, no? So the average which you calculate is going to be the true value, right? So when you measure the true value, right, you will definitely observe some inaccuracy. That also needs to be reported along with your answer. That is what we are seeing. So there would be some inaccuracies in the measurement, which must be mentioned along with the result, which is a true value, right? So the inaccuracy in that measurement is what is given a name called as error, right? So in physics, if you try to speak about the errors, right, they're basically classified into two types. What are they? One is the systematic error, and the second is going to be random error. Are you able to understand what I'm saying? Right? So the inaccuracies should be reported along with the result, and those inaccuracies are called as errors, and errors are basically classified into two types. What are they? Systematic and the random errors. So make a note of this point. Yeah, this book is yours, sir. உனக்குன்னு பார்த்து எப்படி ஒரு புக் வந்துருக்கு? ஏன் அப்படி ஆச்சுன்னு தெரியல. நான் பார்க்க I gave him maybe when they cut it got I for detail. I for detail சொல்லுவாங்க அது. Yeah, shall I proceed? Yes. Now we'll see what are these types of errors in detail. So first thing that we are going to see is systematic errors. So systematic errors are those errors that tend to be in one direction. So unidirectional errors are said to be systematic errors. That is, they can either be positive or negative. If it is zero, that's not called as an error at all. So it can either be positive or negative. Let me give you a perspective of what it means. See, suppose I give you a weighing scale, right? An analog one, not the digital one. So you will have the pointer here. Let's say it is at 0. Right? As soon as someone stands on top of this, what will happen? It will start rotating. It will stop at a particular value. It will first oscillate, then it will stop. Because there is a spring, because of which it will oscillate. But it is going to stop, right? So that is okay. That is going to give you a reading. Let's say the reading comes out to be 60. So 60 kilogram. What is the measurement it is giving me? What is it measuring? So kilogram is, this is what we think. It is actually not giving you the weight, it is giving you the mass. Though it is called as weighing scale, right? Most misused word there. It should have actually be called as mass scale, but we call it as weighing scale. Okay. Right. So it gives you the 60 kilogram, right? So initially what is going to happen? You can report this answer to be 60, provided this pointer is at 0 when no load is present on it. There will be some machines, what will happen is after multiple users, they will start exhibiting some errors, in the sense sometimes the pointer will not be exactly at 0, it will be before 0. So those are called as negative errors. Why we call it as negative errors? See, for example, here you don't know what is the reading. Let's say it is somewhere around 0.5 kilogram on the left of it. Let's assume something like that. Now the pointer is exactly stopping at 60. The weight of the mass of the person is not 60 now. Actually, it is 60.5, because that 0.5 error was occurring. So when you have a negative error to the final reading, you will add it back. Sometimes what will happen is the pointer will be on the right of it. If it is here, okay, it is fine. So if you have a positive error, let's say again it is stopping at 60, the mass of the person is not 60, rather it is 59.5, because initially it had some error. So that is why when you go to shop, right, when you buy some vegetables or something, first what they do is, have you ever observed that? Have you ever been to shops to buy something? Okay, you go to supermarket, do this as an activity. Holidays, help your parents. Yeah. When you pick some vegetables and give it to the person who's going to measure the mass of how much ever quantity you have picked up, no? First, they'll keep the plastic tray. That is because they'll not directly put it on the weighing scale. You observe it. They'll keep that plastic tray that also has some mass. So first, what they will do is they'll calibrate the machine in such a way that the mass of the plastic box is removed. If that is not removed and they add mass to it, right, they're actually cheating. Because let's say you picked up 1 kilogram, but this is somewhere around, let's say 100 or 200 grams of something like the plastic. So you're losing 200 grams of whatever quantity you picked, and you're paying unnecessary. So whenever you see, right, you need to observe. That's a digital scale, and you'll be able to see from both the sides. So first they have to make it 0. First they'll keep the plastic box, they'll subtract it, it will become 0. Then they will start adding the mass which you have done. See, for example, if they measure what you do is, let's say you pick 5 vegetables, right? First they put potatoes, because the harder ones are put at the bottom. That's the logic. Okay, they put it, no, then you will have some value out of it. Then what they will do is again make it 0, so that when you add next vegetables onto it, again that value will get added. So you're able to understand what I'm saying. So this is how they need to do the measurement. Next time, observe. They calibrated it. Machine is already calibrated, right? So if the same, Maybe they see if that mass is kept, maybe they've calibrated. I don't know how that machine works. So I can't comment on that because I'm not from that side. I'm assuming that the machine already knows if this mass is placed, you have to make it 0. Okay. I'm not sure. I might be wrong also. But what I'm trying to say is this should happen. Huh? Even maybe that value is removed already. That mission, maybe it has some better understanding capacity. Okay. So it has an understanding capacity, and then you put that mass, it understands. Okay. It will have. There is nothing like it will not have. You place your finger and see, you will be able to see. You will feel as if you have not applied pressure, but you will see some mass. It will happen. When something is applying pressure, definitely there. Okay. At least few grams of therino, or else that machine should have been in such a way that on the grams calculate it might be the precision of that instrument that it will not measure that value at all. In the minimum 25 grams it will be measuring. So yesterday I went to actually buy some weighing scale for some experiments. That time he asked me one question: what is the least value you want to measure? So I told 25 grams. So measure he asked me. I told no, as of now. So what I wanted to do is I wanted to take some powders and prepare a small experimental kit. Let's say I want to put 10 grams of some baking powder into something. I need a device which will actually measure the 10 grams and give me, right? Now 25 grams, what is the loss I'm going to face? I cannot measure 10 grams because least value itself is 25 grams. The practical purpose. So when you do something like this, right, you will have these kind of errors occurring because of the calibration, or something could have happened to that machine also. We don't know, right? Second is, such errors cannot be both positive and negative simultaneously. Obviously, right? It cannot happen. It has to be unidirectional. That is why it has to either be positive or negative. So let's see some of the sources of systematic errors. The first one is instrumental error. Just now I told you, weighing machine is an instrument. It has some error associated with it, right? So this type of errors arise due to the imperfect design, or now you are able to understand this word calibration. So how the device is calibrated. So improper calibration of the measuring instrument. For example, let's take that scale only. So generally what should happen? You buy something and come. You're not going to sit like this, take a microscope and check if every reading is perfect. As a consumer, what you'll do? You'll buy from the shop and come. Suddenly you're doing one experiment one day, you observe some error. The error is at one place, the distance between two lines. So at most of the places, the distance between two lines is 1 millimeter. Suddenly you observe one thing, that the distance between two lines is not 1 millimeter. It is either less than that or greater than that. Then what is it your mistake? That is a calibration mistake. So the machine made that mistake. So that's what is an example of instrumental. You're able to understand. See, every time you will not have eye for the detail. Like every time you cannot catch it. But sometimes when you do, at some point you will do it. You will be able to catch it. So that is the meaning of improper calibration of the measuring instrument. Okay. Next is, this is one I told you. When no object is suspended from a spring balance, you know what is a spring balance, right? You've seen it, no? You just hold it like this. The spring will be hanging. It will come down. So one side you will have mass, the other side you will have force. One side will be mass, other side will be weight. So one side kilogram, one side Newton. Like how this is there. One side centimeter, one side inch. No? Like that will work. So when no mass is suspended, right? If suppose the pointer shows 0.1 gram instead of 0, then what is the meaning? Is there an error or not? Yes. So your 0 starts at the top. So instead of 0, it is showing somewhere over here. What do you think would be the reason of that error occurring? If you see initially while buying itself, you have that error, that is a calibration problem. But after multiple uses, what would have happened is the spring would have lost its elasticity. That's why it's called a spring balance. So spring would have lost its elasticity, where it is not able to go back to its original state after the mass is removed. Or sometimes what you will do, you would have connected something more than the load. There'll be a reading, 0 to let's say 100 grams is what you can connect. You can suspend. Suppose you suspend 250 grams, remove it, what would have happened? The spring would have lost its elasticity. So sometimes that kind of errors can also occur. When no object is suspended, there will be an error that is going to occur. Right? then all the measurements of more than true weight will be systematic. So will systematically contain the error during the experiment. So obviously, right, when you measure, for example, 50 grams in this, is the answer going to be 50? How much is it going to be? It will be 49.9, provided it was a positive error. Sorry, provided it was a positive error. Or else it would have been 50.1 had it been negative error. They told 0.1 gram, they didn't say it is positive error or negative error. So negative is in this case, in this kind of devices where 0 is the least value that you can see. Something above that you cannot tell what is the accurate value. You will only be able to guess it. நான் சொல்ற புரியுதாடா? 0 இங்க இருக்கு. Below 0 you have the numbers. Above 0 you don't have numbers. So below 0, if it is 0.1 gram, is you can say okay, 0.1 gram is there. Above you cannot. You will only guess it. So negative errors is slightly difficult to handle. And you will have these kind of errors. Why I'm stressing on this point is this kind of error will definitely occur in your lab because you're not the only person using it. Somebody wants to, they want to play with it and they have spoiled it. If you get that wrong equipment in your hand, then you should be in a position to say whether that equipment is going to give you the right value or not. Or else you'll be breaking your head that my answer is not matching with someone else. You'll be wasting your time also. So the first thing you need to understand is you need to have that eye. You need to check, okay, whether this device is right or not. So that is one thing I would like to put in your mind, stating for your 11th and 12th, right, concentrate, because one of the useless things on the planet is your lab. Second useless thing is your lab manual and record work. You will be asked to waste your time on that. You're already wasting time. Don't waste the time in lab also. Seriya? I've seen people wasting their time. Instead, you can focus on something else and do bigger aspects. So, you guys watch movies, sir? Mudal Vanna Bhadrakinga, Arjun.
Sir.
Shankar's movie. In Bhadrakinga, yes, sir. You guys watched Bhadrakinga? Mudal one. You watched, no? So he becomes one day CM. You saw that? Which language? Telugu, Hindi, Malayalam? You watch Hindi? Even I'm asking you only. No, you don't watch movies at all. You do? Okay, I don't know how to say. Mudalvan, I don't know what is in Malayalam. Hindi, Nayak, there is a movie, Anil Kapoor's. He becomes one day CM. Have you heard of that movie? He becomes one day CM. What he will do is immediately fall on the system and try to find the faults and remove people. So those who are trying to cheat people, right, he will remove them from the job. Whether it is a government official, even if it is a street vendor, he will remove them. So in that, in one of the scenes, what will happen is you have this physical balance, right? One guy will stick magnet at the bottom. So if somebody has to measure, you would have seen, right? They place 500 gram stone on one side. You place the quantity of whatever substance you want on the other side. It will, when it exactly gets balanced, when the pointer exactly stops at the middle, okay, we'll buy that product. What they will do is they will cheat. They'll keep magnet on one of the sides so that the mass will be more, so that they can give you lesser quantity of that item. They'll cheat. That is also an error. Error in terms of physics, fraud in terms of fraud. That is not mission's mistake. That is okay. அதெல்லாம் கரெக்டா தான் இருக்கும். Physical balance mostly will not have this. And materials are like that. They do it. Yeah, they do it. They do it. Magnetism அதெல்லாம் it works on magnetism. Coil அதுதான் இருக்கும் solenoid இருக்கும். Whenever heat gets generated, whenever current is flowing, you will have magnetism around. That's what you learn, no? Magnetic effects of electric current. That is why they digitalized everything. But still, you can, if you want to cheat, you can cheat, which was their issue. That's why these people came into picture. Ola, Uber, they are controlling those people. Even if you go and not sure if you guys faced issues with auto people. You bargain, no? If you don't go with them, they'll again, you know the way they will treat you, right? Shall I proceed? Yeah. So first type of systematic error is occurring due to the instrument, right? So the second type of systematic error that can occur is because of us. So error due to imperfection in experimental technique or procedure. Means if you are not actually following the exact procedure that you're supposed to follow. Yesterday when experiment failed, you know, that tea bag was supposed to fly. There was an error. So that is because of us. It was sticking, no, I didn't observe that. But second time it worked, right? So error due to imperfection in experimental technique or procedure is the second type of systematic error. See, for example, while measuring the temperature of human body, this is example given here. Any improper contact of thermometer with the body, right, would produce an error in the measurement. So generally, doctors ask you to keep it under your tongue, right? There are other places also, but yeah, mostly we keep it under the tongue. If at all it is touching your tongue, right, then it will show an improper rate. Means your body temperature will not exactly be the same. Okay. So that is one thing. Or else, can you give me another example of where this kind of error can occur? Improper measurements. Let's take the weighing scale only. You kept something on top of it and you want to relax, you stand like this, no, you're done. You also apply weight on it, it will show. Mostly nobody will do that, but I'm saying, as an example, I'm saying. Okay. So these things, external factors like temperature, pressure, humidity can produce systematic errors in measure. So what will happen is even these parameters are going to affect. And other thing that we can, other example we can think of is, did you do Ohm's law experiment last year? So what do? You actually try to draw that graph, no? That VI graph. So you actually calculate the resistance by drawing the VI graph. You take a triangle, calculate the slope, and then do it, right? So actually, what you did is you took the triangle, no, that is actually slope concept, which I taught in the beginning. Okay. So when you do that, right, sometimes what will happen is you will get different value of resistance if the equipment is kept on for a longer duration because of the heating effects of current. Because of the heating effects of current, what will happen is, what does Ohm's law state? Potential difference is directly proportional to current. This is what we state, no? But what is the important point to be concentrated? At a constant temperature. Why are they mentioning it to be a constant temperature? So when you say V is directly proportional to I, you write V is equal to I into R, where R is introduced as what? A constant of proportionality. Means if you remove that proportional symbol, the constant that you can introduce is R. Means you need to keep that R value constant. So what is the value on which R depends on? No. R doesn't depend on V and I. If I give you a resistor, whatever is, it does not depend on the potential difference in the current.
Sir, nature, material, length, and
yes. So R is equal to rho into L divided by A. You know this, right? It depends on the resistivity of that material. See, for example, copper will have a different resistance compared to aluminum or silver, whatever you're going to use. Similarly, it depends on how much length you're taking into consideration, what is the thickness of it. Okay, these are the concepts you would have learned last year, but the most important factor is it depends on temperature also. So if you increase the temperature, resistance of a metal, I'm not talking about other devices, I'm not talking about insulators or semiconductors, resistance of a conductor will increase. So when this happens, right, there will be an error in your Ohm's law experiment. That is the reason why the statement itself starts saying that at constant temperature. So to keep it constant, the best thing that we can do is switch off the device after some time, because they get heated up. As current is flowing through a device, there is something called as heating effect of electric current. No, that is the reason why we do it. Are you able to understand? If suppose you keep the device on for a longer duration and you measure, that kind of an error is due to the imperfection in the experimental technique that you follow. So that is another type of systematic error. And the third type is something related to personal error. So personal error is because of our laziness, we do, let's say we are lazy and we didn't take the measurements properly. See, such an error arises due to the individual's bias. So let's say you pre-assume that this should be the value, you do it, what do you say? You do it with some negligence, or you're careless, okay, in taking the observation, then there'll be some improper readings. For example, let's come to the scale thing. See, suppose I keep it like this. I asked him to measure. You saw what he did. He was trying to go into the scale and see. Without his knowledge, he did it to exactly take what is reading. He could have done another thing also, sat there relaxed like this and told, sir, 21, sir. But he was trying to tell me the exact value. Then I asked him a question, 21.1 or 2 or done. Then he went even more inside. He's trying to act like one microscope. Correct? You did that? No. So he was not careless. Okay. So if suppose somebody else, if you want to be careless, you can sit relaxed and say, okay, 21, so we'll take that. So that is a personal error. Okay, that is one thing. Or sometimes what will happen is there is something called as parallax error. In the sense, if you need to look at this reading, you cannot see it from the top. Due to the refraction or something, you will not be able to see it right. So you need to keep it exactly straight and try to coincide. If possible, keep a small toothpick or something like this, the thinnest device, and try to take the reading, it will be more accurate. If at all you want those kind of precise readings. Okay, that depends on what experiment you're doing. Right. So are you able to understand what I'm trying to say? Right. These are called as personal errors. So what falls under systematic errors? So basically, systematic errors are unidirectional. They can either be positive or negative. They cannot be the same. They cannot be positive and negative simultaneously. Right. And what is the other type of, so why are they occurring? First thing, due to the instrumental error. Second is errors in the errors in the way we perform the experiment. That is the procedure. And the third is procedure in the sense you didn't exactly follow the lab manual. You skip one of the steps, it falls under the illegal. See, that can happen. Sometimes you were sincere, sometimes you would have missed it in a hurry. Okay. So I'm saying what I'm trying to tell you here is, or that could have happened, or sometimes what will happen is it might not be your mistake also. Maybe the procedure given itself is wrong. So you are the one who's following it, you're doing it for the first time. If somebody gives you a wrong procedure and you follow it, that is not your mistake. That is why it doesn't fall under personal error. So personal error is if everything is perfect, because of your own carelessness, you are losing the reading. So there is a minor difference between both, right? So how can you improve the systematic errors? So obviously they are occurring either because of the instrument or because of the procedure or because of your personal error. If you correct either of them, depending on what error you got in that particular experiment, you can reduce the systematic errors. So systematic errors can be minimized by improving the experimental technique or selecting high quality instruments and removing the personal carelessness. You're able to understand? It's a simple concept only, but I'm trying to connect with the real-time example. I hope you could understand this, right? So this is all about systematic errors, and the next one is about the random errors. I'll finish that also. So the random errors are those errors which occur due to the irregular or unpredictable fluctuations in the factors affecting the measurement during experiment. Okay, so random, it's random. It's not because of anything that we know. It's happening because of maybe the nature, right? The random errors are those errors which arise due to the irregular or unpredictable fluctuations in the factors that are affecting the measurement during an experiment. See, for example, let's say there is an experiment you are supposed to do only at 25 degrees Celsius. You need to do it only at 25 degrees Celsius. Suppose you have a room. I've given you a room. But what is there? I try to keep it at 25 degrees Celsius. What is the best I can do? Maybe I can switch on an AC and give it to you at 25 degrees Celsius. I would have done it. But there is a possibility where the temperature is not exactly 20, maybe it is 27. So what has happened? So it could be due to any of the factors. I don't know. Maybe there is some opening, some warmth has come in, some heat has flown. I don't know what has happened, but it's not your mistake. It is randomly occurring, right? Because of the unpredictable situation. So that is a random error. Are you able to understand what I'm trying to say? So these type of errors can be both positive and negative. So such errors can be estimated by taking many observation and then taking their. So what you do is you take you do the experiment multiple times and see whether there is an error or not. Because see, 99% what will happen is when you before you do an experiment itself, you will know that this is the reading I'm expecting. That is a smarter way to do. See, for example, in your textbook, you know the refractive index of water. Okay, refractive index of water, you open the table, you will be able to find it 4/3. So experiment panna enna varanum? 4/3 da varanum. If you get something else, see, you might get a value closer to it, either this side or that side. That is fine. But it should not be too much like it should not come somewhere around 7/5. So for example, 1.33 varana, okay, 1.35, 1.37 accepted, or 1.29, 1.30, it's accepted. Okay, slight error. Adukku vandu 0.5, 0.6 error la irukku. Because when you convert it into percentage, right, we'll be learning about how to calculate errors. When you calculate a percentage, right, it should not be a very big number. 1%, 2%, 3% error is okay. Okay, means so lesser the value of your percentage of error, more accurate your measurements. I'm not talking about precision, more accurate. Accuracy is depending on the measurement you take. So this is all about the different types of errors. I'll just show you one thing. So next is about the estimation of error. This is the mathematical part. So till now, whatever we saw was completely theoretical. Okay. After this, the whole chapter is mathematical. This is the only chapter till here which has this much of theory and I have to speak. Everything else is mathematics. Okay. So make a note of this. Did you finish this slide? So write it down. So if they have finished, click on the next part. Getting error. Yeah. So we'll stop with this. You finished writing? Okay. So we'll wind up this. Those who are there for math can stay back. Okay. Let's see.